Welcome back. If you're an AMT student wrestling with those famously tough final chapters on electricity and electronics in the general course,
Yeah.
well, you know the jump. Going from basic circuits to high-speed digital stuff and those big generators.
It really is a huge leap. You're covering everything from like the physics inside a tiny semiconductor all the way up to the heavy rotating machinery.
Exactly. And this stuff isn't just theory. It's the bridge between knowing Ohm's law and actually being able to troubleshoot the line replaceable units, the LRUs, you'll handle daily.
That's the goal today, right? A focused run through. We want to connect the dots between high power solid state devices, the basics of amplifiers and logic circuits, and then tie it all together with DC and AC generators and motors.
Think of it as trying to build that mental map, connecting the tiny switch in a chip to the massive power turning a landing gear motor.
Right, because diagnosing those complex systems, it absolutely hinges on understanding these fundamentals. So let's dive in, maybe starting with diodes, how those simple one-way streets get specialized.
Sounds good. Tag 2. Advanced diodes and signal conversion, the static switch.
Yeah.
Okay, rectification first. Converting AC to pulse DC. The most basic is the half-wave rectifier, yeah.
Yeah, the half wave, it's simple but really inefficient. It basically just takes one half of the AC wave, say the positive swing.
How does it do that?
Well, during that positive swing, the diode is forward biased. It acts like a closed switch, letting that voltage pass through to the load.
Okay.
But then, when the AC input swings negative, the diode becomes reverse biased. Now it's like an open switch. Zero current flow.
So you get these big gaps in the output power. Not great for aircraft systems that need continuous juice.
Definitely not. That's why you almost always see the full wave bridge rectifier in aircraft power supplies. It's just way better.
Because it uses the whole AC cycle.
Exactly. No gaps. You get a continuous stream of DC pulses. The key is using 4 diodes, usually called D1, D2, D3, D4, that switch roles with each half cycle.
Walk us through that switching. On the positive half cycle, which ones are working?
Okay, imagine the current path. Positive swing means D1 and D3 are forward biased. They let current flow through the load resistor. At the same time, D2 and D4 are reverse biased, blocking current on that path.
Got it. D1 and D3 conduct.
Right. Then the AC input flips negative.
So D1 and D3 shut off.
They become reverse biased, yeah. Now the other pair, D2 and D4, become forward biased. Current flows through them.
Okay.
But here's the clever part, the really important takeaway for you. The way the bridge is wired means the current still flows through the load resistor in the exact same direction as it did during the positive swing.
Ah, so it flips the negative half wave up, making it positive.
Pretty much. It takes that negative swing and routes it so it adds to the positive pulses. Continuous pulsed DC output. That's the magic of the bridge.
Makes sense. Now, these days we think silicon diodes, but that wasn't always the case for high power stuff, was it?
Oh, definitely not. Before modern semiconductors got really good, especially for high power, systems often used dry disk rectifiers.
Dry disk.
Yeah, things like copper oxide, selenium, or magnesium copper sulfite rectifiers. They worked on the principle that joining 2 different conducting materials creates a barrier. Current flows easily one way, low resistance, but faces high resistance the other way.
Same basic idea as a diode, just different materials.
Exactly. The underlying concept, using a junction to allow one-way flow, is the same. Now, of course, for modern aircraft, we're looking at power rectifier diodes. Things like the 1N4000 series handle maybe an amp, but you see others rated for hundreds of amps.
And those big ones always seem to be housed in metal.
Absolutely crucial. That metal case is the heat sink. High current means lots of heat. Remember, PUTO pulls I22RR. Without that metal casing to dissipate the heat, the junction would just burn itself out very quickly.
So if you see a big metal case diode, you know it's handling serious current.
You bet. Now, sometimes the voltage in a circuit is too high for a single diode. Its peak inverse voltage or PIV rating isn't enough.
What's the fix then?
Simple solution, diode stacking. Just like putting resistors in series to divide voltage, you put diodes in series.
So if one diode handles 50 volts PIV, and the circuit sees 200 volts.
You'd need to stack at least 4, probably 5 for safety margin, in series. They share the reverse voltage load, increasing the total PIV the whole assembly can handle. Very common in high voltage power supplies.
Okay, let's move beyond basic rectification to some specialized diodes. Zener diodes first. They're called breakdown diodes. Why make a diode designed to break down?
Well, it sounds counterintuitive, right? But it's a controlled breakdown. Unlike a regular diode failing unpredictably past its PIV, a zener is specifically engineered to conduct current backwards once it hits a very precise reverse voltage.
The Zener voltage.
Exactly. Could be 5 volts, 12 volts, anywhere from maybe up to 200 volts, depending on the design. Once it hits that voltage, it starts conducting heavily, but the voltage across the zener stays locked at that specific breakdown voltage.
So it acts like a voltage regulator, clamps the voltage at a certain level.
That's its main job. It provides a constant voltage reference or acts as a protection device, shunting excess voltage away.
Why do you need two of them, back to back, if you're regulating AC?
Because a single zener still acts like a normal diode in the forward direction it conducts easily. So on its own, it would regulate one half cycle, but just pass the other. To clamp both the positive and negative swings of an AC signal, you need two facing opposite directions.
Okay, now let's talk light. LEDs, light-emitting diodes, are everywhere. How do they make light instead of just heat like a regular diode?
It's all about the semiconductor materials used. In a standard silicon diode, when an electron crosses the junction and recombines with a hole, the energy it releases comes out as heat.
Right.
But in LEDs, they use different materials, things like gallium arsenide or gallium phosphide. These materials are chosen so that when that electron-hole recombination happens, the energy is released directly as photons as visible light.
And the advantages for aircraft are huge. Longer life, lower voltage, less heat.
Massive advantages, especially for instrument panels, warning lights, cabin lighting, much more reliable and efficient.
Then there's the opposite, the photodiode. It detects light.
Exactly the reverse effect. You operate a photodiode with reverse bias. When light strikes the depletion region of the junction, the light energy actually creates new electron-hole pairs.
More charge carriers.
Right. These light-generated carriers add to the normal reverse leakage current. So the stronger the light hitting it, the more carriers are created, and the higher the reverse current flows.
Making it perfect for light sensors, ambient light detectors for displays, that kind of thing.
Precisely. Now, another interesting one is the varactor diode, variable capacitance.
How does that work? I thought capacitance was fixed by physical structure.
Well, remember that the depletion region in any reverse bias diode acts like the dielectric in a capacitor, with the P and N regions being the plates.
Okay.
And the width of that depletion region changes depending on how much reverse voltage you apply. More reverse voltage, wider depletion region.
Ah, so changing the voltage changes the dielectric thickness, which changes the capacitance.
You got it. By varying the DC reverse bias voltage on the varactor, you can electronically tune its capacitance.
Which replaces those old, bulky, mechanical tuning capacitors in radios.
Exactly. Much smaller, more reliable, used all over RF circuits for tuning oscillators and filters electronically.
Cool. Finally, the Schottky diode, known for speed. What makes it so fast?
The Schottky is unique. Instead of a PN junction, it uses a metal silicon junction, like gold or platinum on N-type silicon. It's a unipolar device.
Metal silicon. Okay. Why is that faster?
The key is that this type of junction doesn't really have the same kind of charge storage effect you get in a standard PN junction's depletion region, especially involving minority carriers.
No stored charge means it can switch off faster.
Almost instantaneously. There's very little recovery time needed. This lack of charge storage allows Schottky diodes to switch incredibly fast, up to hundreds of megahertz.
And that speed is critical for what kind of circuits?
High-frequency power supplies, especially the switching mode power supplies, or SMPS, that are common in modern avionics. They switch currents on and off at very high rates. A slow diode would waste a lot of energy during the switching transitions, creating heat and inefficiency. Schottky diodes minimize those switching losses.
Essential for efficient power conversion in compact LRUs, then.
Absolutely. Hashtag tag 3. Transistors, amplifiers, and logic, the processor and controller.
Okay. Moving from diodes, the one-way gates, to the real controllers.
Yeah.
Transistors, the three-legged device that changed everything.
The basic structure is key. Emitter, base, collector. 3 layers, 2 junctions. And the really critical design feature is that the base region is physically much thinner and has much lighter doping compared to the emitter and collector.
Right. And the name transistor comes from transfer resistor. How does that thin, lightly doped base enable that transfer?
It cleverly exploits the difference in resistance between the 2 junctions. You apply a small forward bias to the emitter-based junction that makes its resistance very low.
Okay, easy path for current.
Then you apply a large reverse bias to the collector-base junction. That makes its resistance very high.
High resistance.
Now, a small change in current at the low resistance input, base emitter, causes electrons or holes to cross into the base. Because the base is so thin and lightly doped, most of those charge carriers don't recombine there. Instead, they get swept across the high resistance collector base junction by its strong reverse bias field.
So a small input current controls a large flow across the high resistance side.
Exactly. Since power equals I2 even if the current dollar is similar across both junctions, the power developed across the high resistance collector junction is much, much higher than the power needed at the low resistance base junction. It amplifies power.
Let's trace that in an NPN, the most common type. Electrons are the majority carriers.
Right. Electrons are emitted from the N-type emitter. They easily cross the forward bias emitter-base junction into the thin P-type base.
But most don't recombine with holes there.
Very few do. That small recombination current becomes the base current, I dollars. The vast majority, maybe 98 or 99% of those electrons feel the strong attraction of the positive voltage on the N-type collector applied across the reverse-biased collector-base junction.
They shoot right across the base.
They get accelerated right across that second junction into the collector region, forming the large collector current, IC. So that tiny eyeballer controls the massive IC out. That's the amplification action.
And also allows it to act as a switch. Tiny base current on, large collector current flows. No base current, collector current stops.
Perfect switch. ### B. IC transistor configurations and amplification.
Okay, so to use this device, engineers hook it up in different ways. 3 basic configurations, right? Based on which leg is common.
Correct. Common emitter, common collector, and common base. You identify it by seeing which terminal is connected to or common to both the input signal path and the output signal path.
The common emitter, CE, seems to be the most popular by far. Why is that?
It's the workhorse amplifier. The CE configuration gives you good gain in all 3 areas: voltage gain, current gain, and therefore power gain. The input signal goes to the base, the output is taken from the collector, and the emitter is common to both.
And it has one unique characteristic technicians absolutely need to remember.
The phase inversion, yes. The common emitter is the only configuration that provides a 180-degree phase shift between the input and output signals.
So if the input signal goes positive, the output signal goes negative.
Exactly, and vice versa. If you're troubleshooting a multi-stage amplifier and see signals in phase when they shouldn't be or out of phase, knowing this CE characteristic is critical. 2 CE sages in series should bring the signal back in phase, for instance.
What about the other 2? Common collector, CC.
The CC is often called the emitter follower. The output is taken from the emitter. Its voltage gain is always slightly less than 1, so it doesn't amplify voltage.
Then what's it used for?
Impedance matching and current driving. It has a very high input impedance and a very low output impedance. So it's great for buffering, connecting a high impedance source to a low impedance load without losing signal strength. It's also a good current amplifier.
Okay, and common base, CV.
Common base has the input signal applied to the emitter and the output taken from the collector, with the base being common. It provides good voltage gain, but no current gain. Current gain is always less than 1.
Characteristics.
Very low input impedance and very high output impedance. The opposite of the CC. It's often used in high-frequency applications or sometimes in things like microphone preamplifiers, where you need to match a low impedance source, the mic, to the amplifier circuit. ## see many amplifier classes and coupling.
Amplifiers aren't just about gain, though. Gain is simple. Output divided by input. But fidelity is key, how accurately the output matches the input shape.
Right. Fidelity versus efficiency, that's the big trade-off. And it leads to amplifier classes defined by how much of the input signal cycle the transistor is actually conducting current. This is called the conduction angle.
Class A is first. Full 360-degree conduction. Best fidelity.
The best. The transistor is biased, so it's always conducting, even when there's no input signal. This means the output is a very faithful, undistorted replica of the input.
What's the downside?
Terrible efficiency. Because it's always drawing current, it wastes a lot of power as heat. You might only get 25–30% efficiency. But for applications where accuracy is paramount, like high-fidelity audio or sensitive measurement circuits, Class A is sometimes necessary.
Okay, then Class B improves efficiency.
Significantly.
Hmm.
Class B only conducts for 180 degrees, or exactly half of the input cycle. One transistor might handle the positive half, another the negative half in a push-pull arrangement.
So it's only on half the time.
Right. This doubles the theoretical maximum efficiency compared to Class A, maybe up to 78%. But the output is distorted because each transistor cuts off for half the cycle. You get what's called crossover distortion, where the signal transitions between the two transistors.
Then Class AB is the compromise.
The practical compromise, yes. Class AB conducts for slightly more than 180 degrees, but less than 360. This small overlap period minimizes that crossover distortion you get in pure Class B, while still offering much better efficiency than Class A, very common in audio and general-purpose amps.
And finally, Class C conducts less than half the cycle.
Less than 180 degrees, yeah. Sometimes much less. This makes it the most efficient class, often over 80 or 90%.
But the output must be terrible.
Highly distorted, it's basically just pulses of current. So Class C is only used in very specific applications, mainly radio frequency transmitters. The output tank circuit filters out the harmonics and restores the desired signal shape, but you're leveraging that high efficiency for RF power, ###D, coupling methods, and op amps.
All right, so you've amplified a signal in one stage. How do you get it to the next amplifier stage without messing things up? Coupling methods.
Right. You need to pass the AC signal along, but block the DC biasing voltage of the first stage from affecting the second stage. The most common method is RC coupling.
Resistor capacitor.
Yep. You use a coupling capacitor connected between the output of the first stage, like the collector, and the input of the second stage, like the base.
And the capacitor does what?
Capacitors block DC but pass AC. So the AC signal voltage goes right through the capacitor to the next stage, but the DC bias voltage from the first stage is stopped. This prevents the bias point, the operating point, of the second transistor from being upset.
Simple and effective.
Yeah.
What about transformer coupling?
Transformer coupling is also very common, especially in power stages or for impedance matching. The varying output current of the first stage flows through the transformer's primary winding. This induces a signal voltage in the secondary winding, which is connected to the next stage.
Advantages.
Good power transfer efficiency, and transformers are excellent for matching impedances between stages, like connecting a high impedance amplifier output to a low impedance speaker. They also provide DC isolation naturally.
Okay, now feedback. Taking some output signal and feeding it back to the input, why do that?
Feedback is crucial for controlling amplifier behavior. There are two main types, positive and negative.
Positive feedback sounds bad, like that screeching sound from a microphone near a speaker.
That's exactly what positive or regenerative feedback can cause if uncontrolled. The feedback signal is in phase with the input signal. It adds constructively, increasing the gain. Too much positive feedback leads to instability and oscillation, the squeal, though it can be used controllably in oscillators.
So negative feedback is the useful one for stability.
Generally, yes. Negative or degenerative feedback takes a portion of the output signal and feeds it back out of phase with the input.
It subtracts.
It effectively subtracts, yes. This reduces the overall gain of the amplifier.
Why would you want less gain?
Because in return for lower gain, you get significant benefits. Increased stability, reduced distortion, wider bandwidth, and it makes the amplifier's gain less dependent on the specific transistor characteristics and more dependent on the feedback network components, which are usually precise resistors. You trade raw gain for precision and stability.
Which leads us to the op-amp, the operational amplifier. These seem like fundamental building blocks.
They absolutely are. Usually found as an integrated circuit, an op-amp is essentially a very high-performance differential amplifier. It's characterized by three things: extremely high voltage gain, like hundreds of thousands or millions, very high input impedance, doesn't load the source, and relatively low output impedance can drive loads.
And they have those two inputs, the inverting and non-inverting plus.
Right. A signal applied to the non-inverting plus input appears at the output with the same polarity. A signal applied to the inverting input appears at the output 180 degrees out of phase or inverted.
You use feedback with these.
Almost always. By applying negative feedback using external resistors and capacitors, you can configure the op-amp to perform all sorts of functions: precise amplification, filtering, comparing voltages, integrating, differentiating. They're incredibly versatile. ###she e-tapertize, introduction to digital logic, true-false decisions.
Okay, shifting gears from analog amplification to the digital world. Zeros and ones, true and false. The language of computers.
The foundation of all modern control systems, flight computers, you name it. The first thing to grasp is logic polarity.
How we define true and false with voltage levels.
Exactly. In positive logic, which is common, a high voltage level, like plus 5 VDC, represents a logic 1 or true state, and a low voltage, like 0 VDC or ground, represents a logic 0 or false state.
But there's also negative logic.
Yes. Less common now, but you might encounter it. In negative logic, it's flipped. The low voltage 0 VDC represents true 1, and the high voltage represents false 0. You happen to know which system an LRU is using to interpret signals correctly.
Digital signals are pulses, but they're not perfect square waves in reality.
Never perfect. We need to define the characteristics of a real pulse. We talk about rise time and fall time.
How fast it goes from low to high and high to low.
Right. And specifically, we measure rise time as the time taken to go from 10% to 90% of the pulse amplitude. Fall time is the time from 90% down to 10%.
And pulse width.
Pulse width, or pulse duration, is typically measured between the 50% amplitude points on the rising and falling edges. These timings are critical in high-speed digital circuits.
Let's hit the fundamental logic gates, the building blocks. Simplest is the not-T gate, or inverter.
Dead simple. One input, one output. Whatever logic level is at the input, the output is the opposite. 1 ins, 0 out,
Okay.
0 ins, 1 out. It just inverts the logic state.
Then the AND gate. This starts the decision-making.
The AND gate needs all of its inputs to be high GH, true 1, for its output to be high GH. If even one input is low W, false 0, the output is low W.
Perfect for permission-type logic.
Exactly. Think about enabling something critical, like autopilot engagement might require NAV mode selected, anti-altitude hole engaged, anti-airspeed within limits, and no excessive bank angle. All conditions must be true, logic 1, for the AND gate output to go high and allow engagement.
Okay. The OR gate is more lenient.
Much more. The OR gate's output goes high GH if any one or more of its inputs are high GH. The only way the output is low is if all inputs are low W.
So this is good for warnings.
Perfect for warnings or fault enunciations. A master caution light might come on if engine fire loop A senses fire, or engine fire loop B senses fire, or APU fire loop senses fire. Any single true input triggers the warning.
Then we get the combinations, NAND and NOR.
Right. NAND is simply not AND. It's an AND gate followed by an inverter. Its output is low only when all inputs are high H. Otherwise, it's high H.
And NOR is not OR.
An OR gate followed by an inverter. Its output is low if any input is high H. The output is high only when all inputs are low. NAND and NOR gates are actually very important because you can build any other type of logic gate using only NANDs or only NORs. They're called universal gates.
Interesting. What about the exclusive gates, XOR?
The exclusive or XOR gate gives a high H output only when its inputs are different. So if you have one input high GH and the other low, the output is high H. If both inputs are the same, both high H or both low, the output is low.
So it detects a mismatch.
Exactly. Useful for comparison circuits or binary addition, its counterpart is the exclusive NOR XNOR.
Which does the opposite.
Right. XNOR gives a high GH output only when its inputs are the same, either both high GH or both LOW. It signals equality or coincidence. Tag them in integrated circuits, ICs, and levels of integration.
Okay, building complex systems like a flight computer needs thousands, millions of these gates. You can't wire them individually. That's where integrated circuits come in.
Absolutely. The IC revolutionized everything, putting transistors, diodes, resistors, and connections all onto a single tiny chip of silicon.
Main advantages. Obvious ones seem to be size and weight.
Huge factors in aviation, but also dramatically increased reliability, fewer connections to fail, much lower power consumption, faster operating speeds because signals travel tiny distances, and vastly reduced cost per gate.
And we classify them by how much stuff is packed onto the chip.
Yeah, the scale of integration. Small-scale integration, SSI, might have just a few basic gates, maybe up to 10 or 12.
Okay.
Medium-scale integration, MSI, has maybe 12 to 100 gates. You find things like counters, registers, decoders, more complex functional blocks.
Then it jumps up.
Big time. Large-scale integration, LSI, has hundreds or thousands of gates. Think early microprocessors or memory chips. And today, we're mostly in very large-scale integration, VLSI, and beyond hundreds of thousands, millions, even billions of transistors on a single chip.
Which brings us to the microprocessor, the brain of the system.
The central processing unit, the CPU, it's a programmable LSI or VLSI device designed to perform arithmetic and logic operations based on instructions it fetches from memory.
So it takes inputs, runs calculations, or makes logic decisions based on software, and sends outputs.
Exactly. It's the core component that executes the software programs controlling everything from navigation displays to engine FEDC systems.
Okay.
Hashtag tag IV, DC generators, mechanical power in, DC power out.
All right, let's switch from the tiny world of logic gates back to rotating machinery. Big power. Starting with DC generators, taking mechanical rotation and making DC electricity.
The basic principle is the same as an AC generator, actually. You rotate a coil of wire within a magnetic field. The wire cuts the magnetic flux lines, and Faraday's law says a voltage will be induced in the wire.
But AC generators have slip rings to get that AC out. DC generators use something different.
They use a commutator. This is the key difference. Instead of continuous rings, the commutator is a segmented ring, with each segment insulated from the next. Carbon brushes ride on these rotating segments.
And this commutator does what?
It acts as a mechanical reversing switch. Remember, the voltage induced inside the rotating armature coil is always AC. It naturally reverses polarity as the coil spins through the magnetic field. The commutator's job is to reverse the connection to the external circuit at the exact same moment the internal voltage reverses.
So it flips the negative half cycle, like the bridge rectifier did electronically.
Essentially, yes. It mechanically rectifies the internal AC into external pulsed DC.
Okay, now a really critical concept for technicians. The neutral plane.
Absolutely critical for generator health. The neutral plane is the position where the armature coils are moving parallel to the magnetic flux lines. At this exact point, they aren't cutting any lines, so the voltage induced in them is zero.
Why is that important for the brushes?
Because the brushes are wide enough that for a brief instant as the commutator rotates, each brush will momentarily touch two adjacent commutator segments at the same time.
Shorting out the coil connected between those segments.
Precisely. If there was voltage being induced in that coil when the short occurs, you'd get a massive current surge, causing severe swishing between the brush and the commutator segments. This burns and pits the commutator very quickly.
So the brushes must be positioned exactly at the neutral plane, where the coil voltage is zero during that shorting moment.
That's the ideal. If the brushes are off position, or if something causes the neutral plane itself to shift, you get sparking. That's a major maintenance issue.
This basic setup gives pulsed DC. Lots of ripple, right?
A simple generator with one coil and a two-segment commutator has huge ripple voltage, goes from maximum down to zero and back up. To get the smoother DC needed for aircraft systems, you need more armature coils and many more commutator segments.
More coils fill in the gaps.
Exactly. With many coils, wound at slightly different angles and a multi-segment commutator, the output voltage becomes the sum of many overlapping pulses. This smooths the ripple out considerably, approaching a steady DC value, #tab B construction, and magnetic field control.
Let's quickly cover the main parts, the field frame or yoke.
That's the outer casing, usually heavy iron. It provides the mechanical support for the field poles and, importantly, completes the magnetic circuit for the field flux.
The armature.
That's the rotating part. It carries the armature windings, the coils where voltage is induced, and the commutator. It spins inside the magnetic field created by the field poles.
And the brush assembly.
Holds the carbon brushes, usually under spring pressure, ensuring they make good contact with the rotating commutator segments to pick up the generated current.
Armature windings. They used to be a gram ring type.
Yeah, an older design. The wires were wrapped around an iron ring. The problem was the wires on the inside of the ring were shielded from the main magnetic field and didn't cut much flux, so they didn't contribute much voltage. Kind of inefficient.
So modern generators use.
The drum-type armature. The coils are laid into slots on the surface of a cylindrical core. This way, almost the entire length of the active conductor cuts through the magnetic field, making it much more efficient.
Okay, now a big problem in DC generators. Armature reaction.
Ah, yes. This happens because the current flowing through the armature windings itself creates a magnetic field.
The armature has its own magnetism.
It does, and this armature magnetic field interacts with, and unfortunately distorts, the main magnetic field produced by the field poles.
What's the consequence of that distortion?
The main problem is that it shifts the neutral plane. Remember, the neutral plane is where the induced voltage is zero, and where the brushes should be. If the armature reaction shifts the neutral plane, the brushes are no longer shorting the coils at the zero voltage point.
Leading to sparking.
Exactly. Heavy sparking at the brushes, especially under heavy load, when the armature current, and thus the armature reaction, is strongest. This causes rapid commutator and brush wear.
How do designers counteract armature reaction? Compensating windings.
That's one method, used on larger generators. Compensating windings are actual coils embedded in slots cut into the faces of the main field poles. They are connected in series with the armature winding.
So they carry the armature current.
Yes. And because they carry the armature current, they produce a magnetic field that directly opposes and cancels out the distorting magnetic field created by the armature windings. This effectively keeps the neutral plane from shifting regardless of load.
What about interpoles?
Interpoles are another very common method. These are small auxiliary poles placed physically between the main field poles. They are also wired in series with the armature.
How do they help?
Their windings create a magnetic field in the region between the main poles. The polarity of the interpole is designed to be the same as the next main pole in the direction of rotation. This interpole field counteracts the flux distortion caused by armature reaction in the commutating zone, helping the coil voltage reach zero cleanly as it passes under the brush. Keeps the neutral plane stable. ###see generator types, field winding connections.
Okay, how the main field winding gets its power determines the generator type. Series wound.
Series wound means the field winding is connected in series with the armature and the load. All the load current flows through the field winding.
How does that affect voltage output?
Terribly for regulation. As the load increases, current increases. This stronger field current makes the magnetic field stronger, which increases the output voltage, exactly the opposite of what you want for a stable power source. So, series generators are basically never used for aircraft power.
Aircraft use shunt wound generators more often.
Yes. Shunt means parallel. The field winding is connected in parallel or shunt across the armature terminals. It gets the full output voltage.
How does its voltage behave under load?
The terminal voltage tends to decrease as load increases. This is mainly due to the IR drop within the armature winding itself. More load current means a bigger voltage drop inside the armature, voltage current x resistance. Since the terminal voltage is the generated EMF minus this internal drop, the output voltage sags.
So how do you keep the voltage constant, say at 28 volts?
You need a voltage regulator. Often, this involves putting a variable resistor, a rheostat, in series with the shunt field winding.
Wait, you put resistance in the field circuit to control output voltage? How?
If the output voltage starts to drop, the regulator decreases the resistance in the field circuit. Less resistance means more current flows through the shunt field winding. Stronger field current means a stronger magnetic field, which increases the generated EMF, bringing the terminal voltage back up.
Okay, increases field current to boost voltage. Makes sense. Then there's compound wound.
Compound wound uses both a series field winding and a shunt field winding on the same poles.
Best of both worlds.
Kind of. Usually they are cumulative compound, meaning the series field's magnetism adds to the shunt field's magnetism. The series field provides some boost as the load increases, which helps counteract the voltage drop from armature resistance and armature reaction.
So it gives better voltage regulation.
Much better, especially under varying loads. Depending on the strength of the series winding, you can get flat compounding, voltage stays constant, under compounding, slight drop, or over compounding, the voltage actually rises slightly with load. Used where stable voltage is really critical. #VC motors. DC power in, mechanical power out.
All right, let's flip the process. DC motors. We put DC electricity in, we get mechanical rotation out. Torque. #A. The physics of torque.
The fundamental principle is the motor effect. Put a wire carrying current into a magnetic field, and the wire experiences a force. The force is perpendicular to both the wire, current direction, and the magnetic field lines.
So in a motor, we feed current into the armature windings, which are sitting in the magnetic field from the field poles.
Exactly. That current creates a force on the armature wires. Because the armature is free to rotate, this force creates torque, causing it to spin.
And we use the right-hand motor rule to figure out the direction, or sometimes called the left-hand rule.
Yeah, the naming can be confusing, but the principle is the same. If you point your index finger with the magnetic field, north to south, your second finger with the direction of current flow in the wire, then your thumb points in the direction of the force, the direction the wire will move.
The commutator's role here, still essential.
Absolutely essential for continuous rotation. Just like in the generator, it acts as a reversing switch. As a particular armature coil spins around and reaches the point where the torque would naturally reverse, the commutator segments connected to that coil swap brushes.
It's reversing the current in that coil.
Right. Reversing the current in the coil reverses the direction of its magnetic field. This ensures the force continues to push the coil in the same rotational direction. Without the commutator, the armature would just oscillate back and forth or lock up. #B. Counter electromotive force. counter EMF.
Okay, here's a really important concept for motors. Counter EMF, or back EMF. Why doesn't a DC motor just draw enormous current all the time, given its low armature resistance?
This is the motor's built-in regulator. As soon as the armature starts spinning within the magnetic field, it starts acting like a generator itself.
It generates its own voltage.
Yes, the spinning conductors cut the magnetic flux lines, inducing a voltage according to Faraday's law. This self-generated voltage is called counter EMF, or CEMF, and crucially, Lenz's law dictates that this CEMF always opposes the applied voltage that's driving the motor.
So the voltage actually pushing current through the armature is the applied voltage minus the counter EMF.
Exactly. The effective voltage across the armature resistors is VIV applied VCEMF, and the amount of CEMF generated is directly proportional to the speed of the motor.
Faster spin, higher CEMF.
Right. So when the motor first starts, speed is 0, CEMF is 0. The only thing limiting current is the armature's very low resistance. That's why you get a huge starting current surge.
But as it speeds up,
CEMF increases. This increasing opposing voltage reduces the convective voltage across the armature, which reduces the current drawn from the source. VFNS. The motor settles at a speed where the CEMF is just right to allow enough current for the required torque, but no more.
and that explains why a stalled motor is so dangerous.
Absolutely. If the motor stalls, its speed drops to 0. CEMF drops to 0. Suddenly, the full applied voltage is across that tiny armature resistance. Current skyrockets, and the windings overheat and burn out very quickly unless a fuse or breaker trips. CEMF is essential for normal operation. Hashtag CDC motor types and applications.
Just like generators, motors come in series, shunt, and compound types based on the field connection. Series DC motor.
Field winding is in series with the armature. This means the same high starting current flows through both, creating very strong magnetic fields.
Resulting in
Extremely high starting torque, the highest of any DC motor type. That's why they're used for jobs needing a massive initial grunt. Engine starters, landing gear actuators, flat motors, cowl flaps.
What's the downside? Speed control.
Very poor speed regulation. The speed varies dramatically with the load. And crucially, if the load is suddenly removed, like if a starter shaft breaks, the motor can theoretically accelerate to destructive speeds because there's no load to keep the speed down and the CEMF up. Series motors must be securely coupled to a load.
Okay. Shunt DC motor.
Field winding is in parallel, shunt with the armature, connected directly across the supply voltage. This means the field current, and thus the field strength, is relatively constant regardless of the load on the motor.
And then that leads to
Good speed regulation. Shunt motors maintain a fairly constant speed from no load to full load conditions. Their starting torque is lower than a series motor, but they're used where consistent speed is important, maybe for fuel pumps or ventilation fans.
and compound DC motor.
Uses both a series field and a shunt field, usually cumulative compound where the fields aid each other. This gives it higher starting torque than a pure shunt motor, but better speed regulation and safety than a pure series motor. It's a good compromise for applications with heavy changing loads where you need decent starting torque, but don't want the runaway risk. Hashtag tag D motor control and maintenance.
Reversing rotation. Critical task sometimes. What's the absolute rule for reversing a DC motor?
You must reverse the direction of current flow in either the armature or the field winding, but not both.
Why not both?
Because if you reverse the polarity of both the armature field and the main field, the relative direction of the forces stays the same. The motor keeps turning the same way. You have to reverse just one or the other to flip the direction of the torque.
Methods for doing that.
Common methods include using a reversing switch arrangement, like a DPDT switch, to swap the connections to the armature, or sometimes using a split field winding where you energize one half for one direction and the other half for the reverse.
Speed control in a shunt motor. This one feels backwards. To make it go faster, you increase resistance in the field circuit.
It seems counterintuitive, but it goes back to the CEMF balance. You add resistance, using a field rheostat, in series with the shunt field winding.
Okay, that reduces the field current.
Right. Less field current means a weaker main magnetic field. Now, the armature spinning at its current speed in this weaker field generates less counter EMF,
Lower CEMF.
lower opposing voltage. So the effective voltage across the armature momentarily increases. This causes the armature current to increase.
More current means more torque.
Yes, the temporary increase in torque makes the motor accelerate. It speeds up until the CEMF, generated in the now weaker field but at a higher speed, rises back up to nearly match the applied voltage again, establishing a new, faster, stable operating speed.
Wow. So weaken the field to speed up the motor. Got it. Maintenance points commutators again. What should AMTs absolutely not use?
Never, ever use emery cloth or steel wool on a commutator or brushes. Emery contains conductive, abrasive particles that embed in the soft copper and the insulating mica. This creates shorts and continuous sparking.
What should be used?
Only approved commutator cleaning stones or very fine sandpaper designed for electrical work, and always clean away all dust thoroughly.
And the high mica problem.
Mica is the insulation between the copper commutator segments. It wears slower than the copper. If it starts to protrude above the level of the copper bars, it lifts the brushes off the copper, interrupting the contact.
Causing sparking and poor performance.
Exactly. The fix is called undercutting the mica. You use a special tool to carefully machine the mica down slightly below the surface of the copper bars, typically by about 132nd of an inch. This ensures the brushes ride smoothly on the copper, #tag C6, AC motors, high-speed aircraft power.
Okay, let's shift to AC motors. Increasingly common in modern aircraft, right? Advantages.
Generally simpler construction, especially induction motors. Often no brushes or commutator, which means less maintenance, more reliability. They tend to be lighter for the same power output, and their speed is inherently tied to the AC frequency, making them good for constant speed applications. #tag AC motor advantages and speed.
That speed connection. The formula is speed in RPM equals 120 times frequency divided by the number of poles.
That's the one for synchronous speed. And since aircraft power is typically 400 hertz,
That means high speeds.
very high speeds. A simple two-pole motor running on 400 hertz wants to run at 420 times 2 equals 24,000 RPM. Even a four-pole motor is 12,000 RPM.
Wow. That's fine for fans maybe, but what about heavy loads like landing gear?
Way too fast. So for those high-torque, low-speed applications, AC motor systems will always incorporate a substantial reduction gearbox to convert that high motor speed down to a usable output RPM. You'll see the motor itself might be relatively small, but the gearbox attached is quite large. #tag B induction motor principles.
The workhorse AC motor is the induction motor, especially the three-phase type. It relies on a rotating magnetic field.
Correct. The stator, the stationary part, has windings arranged around it. When you apply three-phase AC power to these windings, where each phase is 120 degrees apart electrically, the resulting magnetic field isn't stationary or just pulsating. It actually rotates smoothly around the stator bore.
Like a magnet physically spinning.
The effect is exactly like that, yes. The speed of this rotating magnetic field is called the synchronous speed, determined by that formula, 120 FP.
And the rotor inside is usually a squirrel cage.
Very common design. It's basically heavy copper or aluminum bars embedded in a laminated iron core, with the ends of the bars shorted together by conducting rings. No electrical connections from the outside.
So how does this passive rotor get turned by the rotating field?
As the stator's magnetic field sweeps past the rotor bars, it cuts across them. This induces a voltage in the bars, just like in a generator. Since the bars are shorted by the end rings, this voltage drives a large current through them.
And current in the magnetic field experiences force.
Exactly. The current flowing in the rotor bars creates the rotor's own magnetic field. This rotor field interacts with the stator's rotating field, producing torque that drags the rotor around, trying to catch up with the rotating field.
But it can never actually reach synchronous speed, right? There's always slip.
It absolutely cannot reach synchronous speed. This concept of slip is fundamental. If, hypothetically, the rotor did reach the same speed as the rotating field, then from the rotor's perspective, the magnetic field would be stationary.
No relative motion, no cutting of flux lines.
Right. No flux cutting means no induced voltage, no rotor current, and therefore no torque. The motor would produce zero torque at synchronous speed, so the rotor must turn slightly slower than the rotating field.
That difference in speed is the slip.
Yes. The slip is the difference between synchronous speed and actual rotor speed, usually expressed as a percentage. It's this slip that allows the rotating field to continuously cut the rotor bars, induce current, and maintain torque. The heavier the load on the motor, the greater the slip needs to be to produce the required torque. #tag C single-phase starting methods.
Three-phase motors are nice because that rotating field starts them automatically. But single-phase AC motors have a starting problem.
Big problem. A single-phase winding just produces a pulsating magnetic field. It gets stronger and weaker and reverses polarity, but it doesn't rotate. A stationary rotor sitting in this pulsating field experiences equal forces trying to turn it both ways simultaneously. Net starting torque is zero.
So it needs help to get going. One method is the shaded pole motor.
Yes, used for very low torque applications like small fans. Part of each stator pole face is shaded by a heavy copper ring or band.
How does that help?
Current induced in this shorted copper band opposes the change in magnetic flux passing through it. This causes the flux in the shaded part of the pole to lag slightly behind the flux in the unshaded part. This slight time lag creates a weak, shifting magnetic field that's just enough to give the rotor a nudge and start it turning in a specific direction. Very low starting torque, though.
For more torque, like maybe a pump or appliance, you need something better, like a capacitor start motor.
Much better starting torque. The capacitor start motor is a type of split-phase motor. It has a main running winding and also an auxiliary starting winding physically offset from the main winding, usually by 90 electrical degrees.
And the capacitor.
A capacitor is connected in series with this starting winding during startup.
Yeah.
The capacitor causes the current in the starting winding to be significantly out of phase with the current in the main winding, ideally close to 90 degrees leading.
And having two windings with currents out of phase creates
A rotating magnetic field, similar to a two-phase system just for starting. This gives the motor much higher starting torque compared to shaded pole or basic split-phase types.
Does the start winding stay energized?
No, usually not. Once the motor gets up to about 75% of its running speed, a centrifugal switch mounted on the motor shaft opens, disconnecting the starting winding and the capacitor. The motor then continues to run on the main winding alone. Leaving the start winding in circuit would cause it to overheat. Hashtag Tech7. Conclusion and final thought.
Well, that was quite a journey. We went from, the tiny interactions inside diodes and transistors through the logic gates making decisions.
All the way up to the principles behind those big DC and AC generators and motors that provide the real muscle in the aircraft. Rectification, amplification, digital control, torque production, CEMF.
It really covers the whole spectrum you need as an AMT. Being able to troubleshoot a complex avionics box relies on understanding that digital logic and the op-amps.
And tracing a power problem or an actuator failure comes back to understanding armature reactions, slip, counter EMF, and even things like checking for high mica. It's all connected.
It's fascinating how often the most complex systems boil down to exploiting very simple physical contrasts, like the huge difference between forward and reverse bias resistance in a diode or a transistor.
Or the critical importance of that tiny insulating gap of mica between commutator segments defining the neutral plane in a multi-kilowatt generator.
It really makes you think.
So maybe a final thought for everyone listening. The next time you're looking at a component, maybe one that seems simple, consider just how many critical aircraft functions, safety systems, flight controls, power generation might ultimately depend on that single part maintaining its exact electrical state or physical property. That precision, that reliance on the fundamentals, that's really the essence of aviation maintenance, isn't it?